Hi everyone, I'm Zhao from University of Illinois. Today I'm going to present ping loads, taming speculative loads in secure processors. Modern processors are threatened by speculative execution attacks. Consider the following Spectre v1 example. The code snippet has two memory accesses, guarded by a bound check. During the attack, the attacker first mistrains the bound check with valid inputs, which makes it biased towards taken. Then the attacker feeds a malicious input X that exceeds array 1 size. Since the branch has been mistrained, it predicts taken. The processor will speculatively read from array 1 with an outbound X, which can potentially read any secret data from the address space. After that, the secret is used as an index to access array 2. This leaks the secret to the attacker via conventional cache-based side channels. To defend against such attacks, many hardware defenses have been proposed. They protect the execution of vulnerable instructions until they reach their visibility point, which means that they are no longer vulnerable to pipeline squashes that are relevant to the threat model considered. Because hardware defenses usually apply expensive protections on vulnerable instructions, any technique that enables them to reach their VP sooner speeds up all those defenses. To see how VP is used in a concrete defense, let's bring back the example from the last slide, but assume that it now takes a valid inbound X and see how a simple defense scheme, fence, will operate. The fence scheme here delays speculative loads until VP. At first, the branch B1 is not resolved. Both L1 and 2 can be squashed by B1, therefore they are pre-VP and not allowed to execute. Only when B1 is resolved, L1 and 2 reach their VP and can be issued to memory. Depending on the threat model, the conditions of reaching VP are different. For example, under the strictest comprehensive model, for a vulnerable instruction load error reaches VP, we require that all control flow instructions older than error are resolved. Error plus any older instruction cannot suffer exceptions, and error plus any older load cannot alias with other loads and stores, or cause a memory consistency violation. For example, if we assume there are two older instructions, branch B1 and load error 1 in the ROB under the comprehensive model, the load error reaches its VP only after B1 is resolved, plus L1 and error itself cannot suffer exceptions, aliasing, and MCVs. Depending on the implementation, ensuring error is invulnerable to MCV requires it to reach the ROB head or become the oldest load. Both of them happen lately in the pipeline. For simplicity, we assume the former one in the talk. To understand the execution overhead caused by each condition, we measure geometric mean execution overhead of fence on different benchmark suites, and break down the overhead by reasons that delay reaching the VP. The plot here is created in a stacked manner. Each block corresponds to the overhead caused by one condition of reaching VP. From the plot, we can see that ensuring no MCVs causes the most overhead. To improve the performance, we propose pinned loads, a general hardware mechanism that makes loads invulnerable to MCVs as early as possible. The high-level idea is that, when certain conditions are met, ping loads will ping a load error and guarantee that no squashes of error due to invalidations and cache evictions. After pinning, error is invulnerable to MCVs. Therefore, it can reach its VP sooner before reaching the ROB head, which offers better performance. To understand the potential performance gain with ping loads, let's consider an example that has three independent loads. On a conventional unsafe core, all three loads can be issued to memory in parallel. While on fence, each load has to reach the ROB head to issue. The memory access is serialized and happens lately in the pipeline. If we augment fence with ping loads, we can first ping LD1, make it invulnerable to MCVs before reaching the ROB head and issue it. Then we also ping LD2 and 3 and issue them while LD1 is pending. With ping loads, we can quickly pass the VP downstream and issue all independent loads in parallel. Before showing the design of ping loads, let's take a small detour to discuss our threat model. We assume the comprehensive threat model, which means a load has to meet all these four conditions to reach its VP. As I will show later, pinning a load can cause a timing difference. So, to preserve the speculative execution security properties of the baseline schemes, we require that a load error can be pinned only if error has met all the conditions to reach VP, except for ensuring error itself will not cause an MCV. Therefore, consider this example to pin the load error we have to first ensure that there are no exceptions, aliasing, and mispredictions, and also guarantee that LD1 and 2 cannot cause MCVs. This has an important implication, which is loads are pinned in the program order. Load L can be pinned only after LD1 and 2 are pinned. Now let's go back to the design of the pinned loads. The high-level idea is to defer invalidations and prevent evictions to lines that are read by a pinned load. To achieve that, we add extra pinned bits in the L queue. When the line receives an invalidation or is being evicted, the current hardware will snoop the L queue to check if line X is consumed by any load. If so, it might conservatively perform a pipeline squash to avoid potential MCV. In pin loads, we slightly change this mechanism so that if line X is consumed by a pinned load, LQ will deny or defer such operation. Although there are no actual pinned bits in L1, we conceptually say that the line X is pinned and it will automatically unpin once LDX retires. The design of pin loads has two parts. The first part is to defer invalidations, which is achieved by introducing new cache coherence messages to defer remote writes. To do that safely, we have to guarantee that no starvation or deadlock is possible. Because of time limit, the talk will mainly focus on no starvation. The second part is to prevent cache evictions by guaranteeing space in cache and directory. We have two possible designs with different performance complexity trade-offs. To see how we change the cache coherence protocol to delay invalidations to pinned lines, let's start with how a conventional protocol handles a remote write. In this example, we have two cores, and the core 2 tries to write to a shared line which presents in core 1's L1 cache in a shared state. With a conventional protocol, core 2 issues a write to its L1, then its L1 sends a getX message to the directory, tries to exclusively grab the shared data. Upon receiving the getX, the directory sends the data to core 2 and an invalidation message to core 1's L1 cache. Then core 1 will invalidate its own copy and reply acknowledgement to core 2. After receiving the ACK, core 2 finishes the modification and sends unblock to the directory, which ends the write transaction. With pin loads, the first two steps are the same, but when core 1 receives the invalidation from the directory, it checks whether the line is pinned by any load. If it's pinned, which is the case in this example, it replies a new message called defer to core 2, which tells core 2 to defer the current write and retry later. If core 2 receives any deferred information, it aborts the transaction by sending a new abort message to the directory. The directory state is unchanged after it receives the abort, and core 2 will retry later. Compared to the conventional protocol, our changes are only adding new coherence messages and the logic of handling them, without any additional transient states, which simplifies the design. However, the simple design can starve core 2. To prevent that, we introduce a tiny per-core hardware structure called CPT, cannot pin table, which records the addresses of lines that the local core is not allowed to pin at the moment. With CPT, core 2's retry looks like the following. It issues a write to L1 as usual, but the L1 will send out an upgraded variant of getX called getX star, telling the directory that the write request has been deferred once and the request has to receive a higher priority. Upon receiving the getX star, the directory sends an upgraded invalidation to core 1. When core 1 gets the message, assuming the line X is still pinned, core 1 knows that it needs to stop pinning the line X by adding the address of X to its CPT. And from now on, new loads that read from X cannot be pinned. After that, core 1 replies defer as usual and core 2 aborts. This retry fails. Because new loads in core 1 can no longer pin line X, eventually, all the older pinned loads that read from line X will retire and the line X become unpinned. At that time, when core 2 retries, it will successfully invalidate the line and complete the write. When a deferred write finally finishes, the directory sends out an extra message called clear to take core 1 to remove the address of line X from CPT, and core 1 can pin line X again. Note that the clear and remove are not part of the write transaction, they're just maintenance messages. Now let's discuss how pinned loads prevent evictions of pinned lines. The high-level idea is similar to how invalidations are delayed. For example, let's assume we have two loads, LDX and LDY, and LDX hits in L1 and LDY misses in L1. Also, both line X and Y are mapped to the same L1 set. Since LDY misses in L1, when it issues, it will try to evict a line from the set. Let's assume the victim line it picks is line X. To perform the eviction, we will snoop the LQ for line X and find that it has been pinned. Therefore, we deny the eviction and also update LRU bits for line X as it has been accessed. After being rejected, LDY will retry. Because the updated LRU bits, now the line A is picked as the victim, which is not pinned. This time, the eviction is successful and LDY will receive the data. This design has to guarantee that a core cannot pin more lines than a set can hold. Otherwise, deadlocks may occur. To see why, let's consider a slightly different example where we have three loads that read from line XYZ. All three lines are mapped to the same L1 set, and LDX misses in L1. We assume that all three loads have been pinned. Now, when LDX issues its request, it will find that it cannot evict either line Y or Z until one of them is unpinned. However, to unpin either line, LDY or LDZ has to retire, but they are blocked by LDX, who is still waiting for the data. Therefore, we have a deadlock here. To avoid this, we propose two possible designs. The first design is called late pinning. The high-level idea is to receive the data first, which means that it can find space in cache and directory. Then we pin the load. If we bring back the last example, what will happen with late pinning is that the LDX issues first, and it finds space in L1, brings the data back, and gets pinned. After that, LDY issues, and it can also find space in L1 and gets pinned. As for LDZ, when it issues, both lines are pinned by LDX and LDY. But since it's the youngest load, it will not cause deadlock. LDZ will stall until LDX retires and unpins line X, which is slow but safe from deadlock. In late pinning, a load must receive its data before being pinned. The memory access is serialized, but the load can be issued before reaching the ROB head, which is much earlier than it would be in fence. The advantage of this design is simple hardware, but the downside is that the memory access is still serialized. It will have low performance for programs with high L1 miss rates. Another possible design is called early pinning. In this design, we add a small local hardware table called cache shadow table to each core. CST tracks for each set in L1 and LLC directory how many lines are pinned by in-flight loads. For the previous deadlock example, we add CSTs for both L1 and LLC directory. For simplicity, we only show L1 CST here. The hash function used by CSTs makes sure that when line XYZ are mapped to the same cache set, they are also mapped to the same CST set. At the beginning, since there are no pinned in-flight loads, L1 CST is empty. Before we try to pin a load, the hardware first determines the L1 set and LLC directory set where the line maps. Then it accesses CST sets and checks if they can hold the additional pinned line. If it can find space in each cache level and directory, it can pin the line. In this example, the hardware checks L1 CST, finds that it can hold line X, so LDX is pinned. For LDY, because it can also find space in L1 CST, it is also pinned before LDX receives its data. As for LDZ, it cannot find space in L1 CST, so we will not pin LDZ until it can find space, which is slow but safe. Note that the CST for a shared cache requires some small changes in its geometry, which is detailed in our paper. Compared to the late pinning, early pinning allows all independent loads to be issued in parallel as long as they can find space in caches and directory, which means better performance, but it requires extra hardware structures like CSTs. To summarize, pinned loads defers invalidations and prevents evictions to lines that are read by a pinned load. For a load error, it needs to satisfy some conditions to be pinned. For security reasons, we require that error has met all the conditions to reach the VP, except for guaranteeing error itself will not cause an MCV. To avoid starvation, we require that the line that error tries to pin is not in the cannot pin table. To avoid deadlock, we require write buffer has enough entries for all the yet to complete stores older than error, which is detailed in the paper. We also guarantee space in cache and directory with two possible designs, late pinning and early pinning. To evaluate the performance improvement of pin loads, we run both single-threaded benchmark suite like Spec17 and parallel workloads like Splash2 and Prosec on three well-known baseline hardware defenses. Here we show the geometric mean execution overhead over the conventional unsafe core on Spec17 for each scheme. The first scheme is fence. The first bar shows that it has very high execution overhead. The second bar shows that its overhead can be significantly reduced when it's augmented with late pinning. And with early pinning, the third bar, the overhead can be further reduced. The rightmost bar shows the overhead of fence under the Spectre model, where we only consider potential control flow mispredictions. Since pin loads cannot remove overhead caused by that, the rightmost bar is the lower bound of pin loads overhead. We can see that early pinning can reduce the overhead close to its lower bound. The next scheme, bomb, has moderate overhead. Bomb delays speculative loads that miss in L1 until VP. It has high overhead on applications with high L1 miss rates, in which case late pinning cannot effectively handle and offers little speedup. But with early pinning, which can overlap independent loads, the overhead is reduced to around 15%, close to its lower bound. Finally, STT, which performs taint tracking, has the lowest overhead, around 25%, and the late pinning brings it down to 19.5%, and early pinning can further reduce it to around 13%. Overall, with early pinning, we can reduce the execution overhead of all three defenses by about half. To summarize, we find that under the comprehensive model, most execution overhead is caused by ensuring no MCVs, so we propose the pin loads, a general hardware mechanism that reduces the execution overhead of speculative execution defense schemes by making loads invulnerable to MCVs as early as possible. Our evaluation shows that pin loads can substantially reduce the execution overhead of many existing defense schemes by about half. Last but not least, our implementation is publicly available. Thanks for listening.